Okay, so when we did the random walk program, I talked about what would happen if the random walk was unfair, if it wasn't a 50-50 chance to win and take a step to the positive side. You can imagine this as some kind of game of chance, some kind of gambling game. Somebody bets you that if you flip a coin 100 times, for every heads they give you $1, and for every tails you give them $1, right? A kind of silly game that, on average, you should lose as much as you win if the coin is fair. Let's imagine a coin that's unfair. Let's imagine a game where you lose a little more than you win. And this is relevant to every casino game, and every casino is set up so the odds are such that you are slightly more likely to lose it than to win it. Let's see what happens. So we can't use the flip that we used before. The flip that we used before was just an integer that was either 0 or 1, left or right. Well, that's not enough if the probabilities are not 50-50. So we're going to use the math.random instead. Remember, math.random gives you a random decimal between 0 and 1. And so we'll just say if it's a fair game, if it's greater than 0.5, you win. If it's less than 0.5, you lose. And then we can change that fairness to be something other than 0.5. So we actually don't need the random class anymore, and we actually don't need to create this random object anymore because we're not using the random class. So the other thing is this flip is no longer an integer, it's a double. Okay, it's giving us a number between 0 and 1. It's not exactly a coin flip anymore, but I'm going to keep calling it flip just so I don't have to change the variable names I use. But I also want some number that's the odds. What are the odds that it comes up heads versus tails? What are the odds that you take a positive step versus a negative step? Let's call that number the fairness of the coin. And so I'm going to make another argument to my method. I give my method two numbers now. I give it how many times to flip the coin, and I give it how fair is the coin. So a 51% coin would mean I get heads 51% of the time and win 51% of the time. A 49% or 0.49 coin would mean I only win 0.49 49% of the time. Okay? So now my condition for when I win is going to be different. Right? The lower that fairness is, the lower the probability I take a positive step. Right? So if the flip is less than the fairness, I take a positive step. If the flip is greater than the fairness, I take a negative step. Greater than or equal. Well, great, just they can't both be or equal. Greater than. Okay, so say I give it a fairness of 40%, 0.4. I'll only take a step to the right if it's less than 0.4. That's less likelihood than it being greater than 0.4, right? Think about it for a minute if that doesn't make sense. Okay. So now when I call my function down here, I have to give it the odds. So let me create a new double called odds. And we'll start with it just equal to 0.5. Okay? And then I'm going to pass that number to the random walk method when I call it. I'm giving it two numbers. How many steps to take, how many times to roll to flip the virtual coin, and what are the odds of a win, right? Odds of a win is the fairness, okay, what I'm calling the fairness. I think that's right. Let's run it and see. If I make the odds 0.5, it should just be just like before. We'll even make this bigger. We'll make this 1,000. We'll run it. After 1,000 steps, my final position is 8. After 1,000 steps, my final position is 10. After 1,000 steps, my final position is 2. After 1,000 steps, My final position is 28. Why is it never negative? 24. Negative 2. There we go. Negative 2. Negative 6. Oh, maybe it was just coincidence. 32. Negative 36. 66. 46. Negative 60. So it's coming out sometimes positive, sometimes negative. Suppose I made the odds a little bit against me. Suppose I change this to 0.49. So I'm only 49% likely to win, and I'm 51% likely to lose. And I'd run this, I flip this coin 1,000 times. What does it look like? 12, negative 104, negative 26, negative 40, negative 14, negative 50, 6, negative 50, negative 28, negative 42. So notice that with the slightly unfair flip, that's only 49% likely to send me in the positive direction, but 51% likely to send me in the negative direction, I'm getting many more negatives. Not only that, I'm getting many more big negatives, and when I win, it's like 6 or 12. When I lose, it's like 42 or 65. That's how Las Vegas works. All the games in that casino, you are like 49.5% likely to win and 50.5% likely to lose. And even though some people will occasionally win the games, more people will lose the games. Even though you have a certain percentage to win some, you have a much greater likelihood to lose more. And that's why casinos in Las Vegas are giant golden and glass pyramids. That's where all that money comes from. The money comes from the fact that the odds are literally stacked against you in all those games, and they can predict exactly what rate of payout will make sure that they win money, and you collectively, you, all the people playing at the casino, lose money. Which is the only way that a casino could be a viable business. If it was fair, if it was equally likely for you to win money as lose money when you walk into a casino, the casino would not be guaranteed to make money. You can't have a business that operates on probability. The business is based on probability and knowing that the bigger this number gets and the more unfair this number gets, the chance of you coming away with any money gets smaller and smaller. 10,000 trials with a 48% probability, you get negative 370, you get negative 306, you get negative 418, you get negative 686. Imagine these are dollar signs in front of these now. Negative 410, negative 216. Now that it's 48% and I'm doing it 10,000 times, in the long run I'm never winning. 236, negative, negative 338, negative 518, negative 366. Okay? So that is how the probability of the random walk works. If it's slanted even a little bit against you, the bigger n gets, the more likely you are to wind up in the negative. If it's slanted slightly towards you, 51%. Okay. Now, 176, 376, 192, 232. Okay, so if the odds are stacked slightly towards you, in the long run, you're very likely to lose. If the odds are stacked against you, in the long run, you are, did I say that right the first time? If they're stacked for you, in the long run, you're very likely to win. If they're stacked against you, in the long run, you are very, very likely to lose. Even if this percentage is small. If this percentage is 49.9%, 0.499. So the chance of you losing is only 0.1% more than the chance of you winning. If this number gets big, which it is if there are thousands of people coming through a casino every day, the chance that the casino loses is very small. Negative 454, negative 304, negative 86, negative 246, negative 666. Okay, so this difference doesn't have to be very big in the odds if the number of people playing, if the number of coin flips, and you can think of every time somebody plays a game in a casino as like flipping an unfair coin. As long as that number is big, as long as the casino is doing good business, at the end of every day they come out ahead. And that's how the random walk applies to gambling as well as physics.